Okay, so Assalamu alaikum wa rahmatullahi wa barakatuh once again. Today we are going to continue the third session in foundation design. If you remember, Ms. Mazoon Al-Araimi has taken with you an introduction or the basics of choosing different types of foundation and then initial thoughts of foundation design. And then in the last lecture, I have taken with you the design consideration that we have to take when it comes to isolated foundation design. And if you remember, we have talked about bending, where bending occurs, and we have talked about one-way shear and two-way shear as well. Okay, so we are going to continue whatever we have started in the last class. We have stopped, I believe, in a certain problem. Are we able to see the screen? Okay. Okay. So you can see here in this particular problem. Okay, you can see here in this particular problem that it says for us we need to check the suitability to have an isolated or combined footing for the encircled columns below, knowing that the safe bearing capacity of the soil is 150 kilonewton per meter square. And let's say I have just slightly modified the question in such a way that it's going to be the shortest side rather than saying the width, because width is going to be normally confused whether it comes like the shorter direction or the longer direction. So I have kept it to be the shorter side of the foundation is restricted to be 2.1 meter. Dead and live loads acting on the columns are 1000 kilonewton and 300 kilonewton respectively. Okay. So what do we have? We have a certain problem that we need to tackle. This is my problem. Okay. So once again, okay, what we need to do, we need to check whether isolated should be used or a combined foundation should be used in this particular location. Now, for us to check whether it's going to be isolated or combined, we need to check whether these foundations, the isolated foundation, are going to overlap or not. So first, what we need to do, we need to figure out the area of an isolated foundation for each and every column. Okay. So let's take one of the columns. Let's say that this is going to be column number 1, for example. So now for column number 1, this is my column. If we are going to place an isolated foundation for this particular column, okay, so this is my section, and then we have a certain length and width when it comes to the plan here. Okay. Now what we know that there are two loads which are acting as dead and live. Now in this problem, they have not specified for us whether they are talking about only the loads on the column or that's including the surcharge, the backfill, okay, including other things or not. So they have clearly only said dead and live load, and that's the only thing to be taken. But when we are designing for a foundation, everything to be taken into account. Okay. So dead and live loads are equal to 1000 plus 300. 1000 for dead, 300 is for life. Now, what we said, we need to calculate the pressure. Okay, we need to calculate the pressure. And for us to calculate the pressure, we say pressure is equal to force divided by an area. Okay. And what we want to get from here, we want to get our area. So my area is going to be force divided by pressure. Okay. Are we okay with this equation? Are we clear till now? Am I talking very fast or is it okay? Are we fine?
Repeat, Mr. Please.
Which point?
The dead load and live load.
Dead load and live load has been given in the problem. This is 1000 and this is 300. Are we okay?
Yes, Mr. Okay, thank you.
So once again, we said that for us to get the area, we need to get the force divided by the pressure which can be taken by the soil. So for me, the force that are going to be taken are equal to 1000 plus 300. These are my life load. The pressure, the soil can take up to 150 kilonewton per meter square. Okay. Now, one thing to be taken into account, this dead and life load of the column does not include self-weight of the foundation. And normally self-weight of the foundation is taken as 10%. We are assuming that the self-weight of the foundation is 10% of the load as an approximation. Okay. So what I can say that now I have 1000 plus 300. This is the load coming from the column multiplied by 1.1. Now this 1.1 includes 1000 plus 300 plus 0.1 into 1000 plus 300. Okay, so it is like we are multiplying the dead load and live load plus 10% of the dead load and live load. So directly you can multiply by 1.1. Okay, now if we get this particular area, you can see it's 1000 plus 300. We are multiplying by 1.1, so we have got it as 1430. Okay, so 1430, the unit is kilonewton, divided by 150 kilonewton per meter square. So now kilonewton will be going with the kilonewton, per divided by meter square will go up. Okay, divided by meter square will go up, so that's why it's an area. Okay. So 1430 divided by 150, that's going to give you around 9.533. Okay, 9.533. So that is the minimum area. That's the minimum area that we can take in order for us not to exceed the maximum capacity of the soil. Okay, for that particular loading. If my area is lesser than 9.533, what will happen? the loading is going to be more than the capacity of the soil. For instance, or for example, if I have 1430, my area of the foundation, let's say that it was 9 only. So I have now force divided by area, which will give me the stress or pressure. So 1430 divided by 9 is going to give you it is going to give you 158. Now we said the maximum capacity can be taken by the soil is only 150. So if you are taking an area of 9 meter, you will see that your soil is going to fail. Why? My soil can take up to 150, but the pressure caused by the loading and the self weight is 158, which is more than the capacity of the soil, so it will fail. How to avoid that? We are avoiding it by increasing the area. From the beginning, not to fail, you shouldn't take something lesser than the minimum area. The minimum area, according to the safe bearing capacity, is 9.533. So any value you will take lesser than that, your foundation is going to fail in ground pressure. So what we are going to say, okay, area is equal to width into length width into length. Now, where it has been mentioned, then one of the dimensions to be 2.1. Okay, one of the dimensions to be 2.1. So my area, let's say 9.533. Let's say the width is 2.1, one of the dimensions, and the other dimension is going to be, let's say, the length or the width. It does not matter now till we know the values. Okay. Now, if we try to find the length, in this case, it is going to be 9.533 divided by 2.1. Can you give me these values? Can you give me this value? 4.539. Okay, 4.539. You shouldn't reduce anything. Okay. Now for me, I cannot take 4.539 because that's not something which can be measured in the site. I cannot have 4 meter 539 millimeters. It's not something practical to be used in a site. Okay, so we can say adopted foundation is 2.1 multiplied by 4.6 meters. Okay, why we have taken it 4.6? Once again, normally we have the foundation rounded to the nearest 100 millimeters because that's something which is easy to be measured in a site. Okay, so now my foundation is 2.1 into 4.6. I need to check that this 2.1 into 4.6 should be more than this value, which we have said earlier. So 2.1 multiplied by 4.6 is going to give you 9.66, which is more than 9.533. So what we try to do, we try to take the parameters given in the question. The parameters given that we have two columns near to each other. We need to check whether it's isolated or combined foundation. Okay, isolated or combined foundation. They have said for us the soil can take up to 150 kilonewton per meter square, which is the capacity of the soil. One of the dimensions is 2.1 meter. Dead and live load has been given as well. Okay, so what we try to do, we try to find first the area for one foundation, for one column, and then we are going to check whether it will overlap or not. Okay, so now if you see here, if you see in this particular drawing, we have section and we have plan. Now you can see the orientation of the column. The column is going to go in this direction. Okay, you can see that this longer side should go with the longer side of the foundation. Okay, the longer side of the column to avoid the moment. Okay, the longer side of the column should go with the longer side of the foundation. Okay, so what is the longer side of a foundation? Longer side of the foundation is going to be 4.6 meter, and the shorter is 2.1 meter. Okay, so once again, the longer side of the column will go with the longer side of the foundation to reduce the effect of the moment happening. Are we clear till now? Are we fine? Are we okay with finding the area for one foundation? Okay. Now, since we have found for one column foundation, we are going to go for the second one. Okay, we are going to check for the second one. Now, if you see in this problem, we have two columns. The distance between two columns is 600 plus 600. So we are talking about 1,000 we are talking about 1,200. Okay, we are talking about 1,200. So if we return back, okay, if we return back, I'll just draw. Now this is my column. This is my second column. The distance between these two, from the center to the center, has been given as 1,200. Okay, has been given as 1,200. Now I have found that the foundation for the first one is 2.1 into 4.6. So I have just drawn okay, where this is okay. Let me just okay, where this is 4.6 meter and this is 2.1 meter. Okay, now if you see the distance from the center of the column, which is the center of the foundation, till the edge of the foundation is equal to 2.1 meter divided by 2, which is half. So we are talking about 1.05 meter. So this is 1.05 meter. The other side is 1.05 meter. Are we okay with that? Are we okay with that? Okay. So we have drawn for the first column. We are going to go for the second column foundation. Okay. Now the same loading, everything is the same. Okay. We are going to just block the new foundation. Okay. So I wrote the second foundation, which is exactly the same since the loading is the same. Once again, my length is 4.6 meter. My width is 2.1. Once again, 1.05 and then 1.05. Okay. Okay. Now to zoom in, you will see that we have this column. Okay. The distance between them once again is 1.2 meter. The first foundation from the center is going to take a distance of 1.05. The second one is going to take from the center is going to take another distance of 1.5. Now can you see that this is 1.05 meter and this is 1.05 meter? If you add these two, 1.05 meter plus 1.05 meter, it will give you 2.1. It means for me the minimum span or the minimum length required for these two foundations not to overlap, okay, not to enter into each other. At least I need 1.05 for this foundation, and I require another 1.05 for the other foundation. Okay, so it means that I require around 2.1 meter minimum length. Okay, if it's more than 2.1 meter, they will not overlap because there is sufficient place for them. If there is lesser than 2.1, then they will overlap. Now in this scenario, how much do I have? How much length do I have? I have only 1.2. Is the 1.2 sufficient to take both 1.05 and then the other 1.05? Is the 1.2 meter sufficient to take both of the 1.05 and then 1.05? No. So what will happen here? You will see that one foundation is going to overlap. One foundation is going to overlap above the other foundation. Okay, one foundation is going to overlap above the other foundation. Okay. So we cannot go and use. Okay, we will just conclude here. Okay. Isolated foundations will overlap, so adopt a combined foundation. Okay, so we cannot go for isolated anymore. We will go for a combined foundation. Okay, we will go for a combined foundation. Now, if we are going to go for a combined foundation, you will see that we have, this is my plan. We have the first column. We have the second column. Okay. And this is the length. And the other side is the width. Okay. So we are talking about this much is your width and this much is your length. Okay. Now, for this particular foundation, what is the loading? What's the loading coming? You will see that there are two columns now. There are two columns. Okay. One is coming from column number 1, another one from column number 2. So I can say that my area required now is equal to, as we said, force divided by safe bearing capacity or the pressure. My force, I have 1000. Okay, 1000 plus 300. Okay. This is for one column. I'm going to multiply it by 2. Okay, I'm going to multiply it by 2 because there are two columns. and then I'm going to add the 10%. There is another 10%. Okay, there is another 10%. Okay, so I'm going to multiply this particular loading into 10%. Okay, so once again, 1,300 from the first, 1,300 from the second. If we go and add these, it is going to be 2,600. Plus the self-weight, which is 10%, will give you a certain value. Okay. Okay. So if I say, for example, if I say 1,000 plus 300, 1,000 plus 300 multiplied by 2 multiplied by 1.1 is going to give you 2,860. Okay. 2,860 kilonewton. Safe bearing capacity is 150 kilonewton per meter square. So 150 kilonewton per meter square. This is the maximum can be taken by the soil. So once again, you can use either this formula, or as we said, if you add these two loads, which are 2,600, 1,000 plus 300 plus 1,000 plus 300, 2,600 multiplied by 1.1, which will give you 2,860 kilonewton. Okay. If we divide it by the safe bearing capacity, you will see that the area is around 19.06 meters squared. Now we know already one dimension has been given as 2.1. So area is equal to, let's say, dimension 1 multiplied by dimension 2. Now dimension 1 has been given as 2.1. My area is 19.06. How much is my dimension 2? It's better to mention dimension rather than width and length. Okay. So now if you see 19.06 divided by 2.1, it will give you 9.07. Okay. So 9.07. Okay, meter, 0.79 meter. Now what we can say that we are going to adopt a combined foundation of 2.1 meter into 9.1 meter. Okay. Once again, you should round up to the nearest, round up, not down. Okay, even if it's 9.01, you should be round up. Okay. You should do the round up. Okay, so it's 9.1 now. Now for 9.1, this is going to be my 9.1. So the length here is 9.1 meter. And then my width is going to be 2.1 meters. Okay. Are we clear about this? Are we clear about the problem and how did we manage to solve it? Are we clear? Okay. Once again, to summarize. Okay, to summarize. First, we should know whether we should know the area for one foundation. So what we have taken, we have got the loading for one foundation. We know the capacity. We know the capacity of the soil. Based on that, we have got the area of one foundation. Okay. After getting for one foundation, I'm going to check Okay, I'm going to check whether it will overlap with the other foundation or not. Now, in this particular problem, foundation number 1 and foundation number 2 are the same. Okay, because the loading is the same for both columns. So your foundation is going to be the same. So we have found one and we have duplicated. Okay, we have drawn it 2 times. One is for the left column, one is for the right column. And you can see between the center to the center distance from one column to another column is 1200. Okay. Now, when we try to combine these 2 foundations, when we try to place the isolated foundations, we have seen that they overlap with each other. Now, since they overlap with each other, we cannot go for an isolated foundation. We went for the other option, which is a combined foundation. Okay. So the whole secret is behind knowing how much is the loading, how much is the capacity of the soil, finding the area for one foundation, finding the area for the second foundation, and then checking the distance from half of let's say the center of the column till the edge of the first foundation, and then the center of the foundation till the other edge of the other foundation, and checking whether these 2 distances, like here, whatever we said, okay, this distance from half of the foundation till the edge, and from the other half till the edge. Okay, this particular dimension or this particular length, whether it is larger than the available distance or not. Now you can see in this particular problem, the dimension required for isolated is 1.05 and 1.05, which is summed up to be 2.1. Now unfortunately, we don't have 2.1. What do we have? We have only 1.2 meter. Okay, we have 1.2 meter, which is not sufficient for the application of isolated foundation. That's why we have shifted to a combined foundation. Are we clear about this problem before we enter to the actual design of the isolated foundation? Any question? Okay. What type of bearing capacity we have used here? What type of bearing capacity is used here? Okay, so Wadha has asked a very good question, which is why we didn't multiply the dead and live load with a factor of safety. Okay, and that's related to your geo. Now, in your geo, you have studied that there are 3 types of bearing capacity. One is safe, another one is ultimate, another one is net. Okay. Anybody can tell me the difference between them? Anybody? It is fine to try. There's no harm of trying. Okay. Now, if you remember, you used to call. Okay. You used to call this to be QS. That's QF, and this is QN. Okay. We have safe bearing capacity, ultimate bearing capacity, and then we have net bearing capacity. Now, you used to calculate the ultimate bearing capacity. We used to calculate the ultimate bearing capacity, and then from the ultimate bearing capacity, we get safe bearing capacity. Okay. So now what we say, my QS is equal to my QF divided by factor of safety. Those who have finished or those who have taken geotechnical engineering 1 or geotechnical engineering 2, sorry, can you correct me here, or this is correct? That safe bearing capacity is equal to ultimate bearing capacity divided by factor of safety. Correct. Okay. Now you will see that already the safe bearing capacity already my safe bearing capacity has been already modified. Okay. My safe bearing capacity has been already modified by a factor of safety. Now, if you multiply by another factor of safety, which is the dead and life load factor of safety, you will see that it will go over the limit. Okay. So one factor of safety has been already multiplied when it comes to the soil. No need to take another factor of safety. Okay. That's why they call this one to be a service limit state condition. Okay. We don't multiply by a factor of safety. Are we okay now, Wadha? The same condition with your deflection. Now, when I say how much pressure is going to be caused by this foundation, then the pressure caused by that foundation is only for the actual loading. Once again, like let's say for example that I have a foundation. Okay, my total loading is 1,200. Now, whether I design it for 1,200 or whether I design it for a factor of safety, and for example being 1,500, okay, my pressure is going to be only for the actual loading which is available. Okay, that's why it's not going to be multiplied as well. And another reason that the safe bearing capacity already has been modified by a certain factor of safety from the ultimate bearing pressure. So you have two reasons. One, that the safe bearing capacity has been already modified. The second reason that the pressure will be caused only by the actual loads, not by the modified loads. Once again, if my weight is 120, my pressure, the pressure going to be caused by me is only for 120. It is not going to be multiplied by a factor of safety. Okay, that's why when it comes to foundation design, area is found based on service limit state. If you remember, we said service limit state is not multiplied by a factor of safety. Ultimate limit state is multiplied by a factor of safety. Okay, I hope that was clear for everyone. Okay. Now we have solved this particular problem. We are going to go for another full design problem of foundation. Now, if you remember, we said that there are 5 things normally we check for RCC elements. Okay. There are 5 things to be checked. We said the first one is durability, if you remember. Second thing, we said bending. Third thing, we said area of reinforcement. Number 4, we said shear reinforcement. Number 5 is going to be deflection. Now we are going to check which one or which of these are going to be applicable. Now, if you remember in durability, we used to check for the water and fire covers, and we used to check for minimum dimension. Now, is fire applicable for the foundation? Is fire applicable for foundation? Do we have any fire when it comes to the foundation? No. Foundation is located at a certain depth where fire will not be there. So we don't need to check for fire. Bending, will there be any bending moment? Yes, there will be a bending moment. So bending moment needs to be checked. If we are having bending moment, do we have minimum area and maximum area of reinforcement? Yes, we are going to be having minimum and maximum area of reinforcement. Shear reinforcement, do we have? Remember last class we have discussed one-way and two-way shear. So yes, of course, there will be shear reinforcement. Now, is the foundation deflecting? Does the foundation deflect? Does the foundation deflect? The foundation will deflect or will settle? Does it have deflection or will it have settlement? Settlement or deflection? Okay, it will have settlement, not deflection. Deflection are for suspended elements. Suspended elements which are hanged, like beam and slab. When we talk about beam and slab, we say deflection of beams, deflection of slabs. When we talk about foundation, we don't say deflection, we say settlement. Okay, foundation will not deflect. It is sitting on soil. It will only settle. It will only go down. It will not deflect. Okay, so there will not be any deflection. Okay, there will not be any deflection. So the things that we are going to check for are durability, in which water is going to be taken into account only. Bending, we are going to check the bending moments, whether it's singly or doubly reinforced. Area of reinforcement, we are going to check the minimum area of reinforcement, and then shear, checking V and VC, if you remember. Now the problem says a 400 millimeter square column carries a dead load of 1050 kilonewton and imposed load of 300 kilonewton. The safe bearing capacity of the soil is 170 kilonewton per meter square at a depth of 1.5 meter below the natural ground level. Design a square pad footing to resist the loading, assuming the following material strength, and the grade of concrete has been given, grade of steel has been given. Now you can see here that the loading has been given as dead and life load only. Okay, and the safe bearing capacity has been given as well. Now I cannot go and calculate my backfilling because I don't have the area of the foundation yet. For me to calculate the backfilling, I should know what is the size of my foundation. Okay, so the loadings which will be taken here are only the dead, life, and self weight of the foundation. If the area of the foundation is known, then you can go and continue calculating the backfill. We will try to see in the upcoming class one problem when it comes to backfill calculation. Okay. Can you just mute yourself, please? Can you all mute yourself? Okay. So we have a minimum grade of concrete, which is C35. That's the minimum grade of concrete for foundation, if you remember. And then we have minimum cover. The minimum cover is, we said, we don't need to go and check. The minimum cover is, we said, if we are going to use BCC, it is from 40 to 50. In Oman, we regularly use 50 mm. And we are always going with the BCC. So when it comes to minimum cover and the minimum grade of concrete, these are almost something fixed for you. So the minimum grade is minimum grade is C35. Okay. The minimum cover is 50 mm. We don't go without BCC. We go with BCC only. So 50 mm. That's the first thing that we have finished from here. So durability now is done. I don't need to check once again for the cover from the table. Cover criteria has been given for you already. Now you can see that we have two loads. One is 1050, another one is 300. So my service loading, we said the loading which is not multiplied by a factor of safety. So my service loading is 1350 kilonewton. Okay, which is an addition of dead and life load. So after finding the pressure, okay, after finding the pressure, we will go and calculate my area. Okay, so the loading, which is service loading with the self weight, is going to be 1485. And how did we get it? We got it by adding 10%. That 10% is reflecting the self-weight of the foundation. Okay, 10% of the loading is reflecting the self-weight of the foundation. So my total loading, okay, my total loading coming from the foundation to the soil is going to be 1,350 plus 10%, which is acting as a self-weight. So now the total is going to be 1,485. To find the area, okay, leave the ULS now, we'll come to it later. To find the area of the foundation, we use the same equation that we have used for the previous problem. So my force is equal to, my area of the foundation is equal to force divided by safe bearing capacity. My force, including the self-weight, is 1,485. Safe bearing capacity has been given in the problem to be 170. So now the area is going to be 8.774. 8.74. Now you can see clearly in the problem, it is a 400 mm square column. Okay, 400 mm square column, and they told us to design a square bed foundation. Now normally if the column is square, it's better to go and use a square bed footing to avoid excessive bending moment. Okay, if it's a rectangle, then it's better to go for a rectangle. If it's a square, then it's better to go for square. Okay, now you can see if my area is 8.74. Okay, if my area is 8.74, and we want to take the root, you will see the root is 9. The under root of 8.74, because it's what you call a square. Okay, it's a square. So the area of the square is going to be b squared, b into b. Okay. So my b now is equal to under root of a, which is in this scenario under root of 8.74, and we have got it to be how much approximately? We have got it to be 2.96. Now we cannot use 2.96, we said. Okay, we are going to be using 3 meters. That's why I have used here 3 meter to 3 meter area of the foundation. Okay, so the adopted area of the foundation is going to be 3 meter into 3 meter. Are we okay till now? Are we okay till now? Anything which is not clear? Everything is fine. So after we have finished from the ground pressure, we have found our area. Okay, we have found our area. We can go and calculate now the remaining thing, which are your bending moment and then your area of reinforcement, and it goes on. Okay. Now, one thing when it comes to foundation design, normally there is no accurate, or let's say, I don't want to say accurate, but there is no simple equation to calculate the depth. So normally to find the depth or to find the suitable depth, normally we assume, and the assumption normally for isolated foundation starts from 400 onwards, so 400 and above. So normally it's better to start with 400, 500, 600. These are the good range of isolated foundation. You shouldn't go lesser than 400. It can go lesser than 400, but to be something practical, keep it as 400. So here in my problem, I have assumed my overall depth of the foundation. Once again, it works as a trial and error. I'll assume a value of the depth, and I'll check whether that depth is going to be sufficient for this problem or not. Okay. So we have it to be 550 mm as a depth. I have assumed it in this problem. We have as well dy, and we have dx. If you remember, there's something similar to slabs. If we want to calculate dx, it is going to be d minus cover minus diameter over 2. D has been already assumed to be 550. Cover, we have got it from the beginning of the problem to be 50 mm. Okay, now the diameter. Now, if you remember, in slabs we have assumed the diameter to be 10 mm. Here we have assumed the diameter to be 20 mm. Anybody knows why? Anybody knows why I have tried to increase? Which element is carrying more load, do you think? Is it foundation or is it or the slab? Which one is carrying more load, slabs or foundation?
Foundation.
Okay. So now foundation is going to carry more loads. If the foundation is going to carry more loads, then of course eventually bending moment is going to be higher. Because we said whenever the load is increasing, the bending moment will increase. Whenever bending moment will increase, your reinforcement will increase. Whenever your reinforcement will increase, your diameter will increase. Do you agree with me? Do you agree that it's a sequence? Loading is higher, loading will cause bending to be higher, bending will cause area of reinforcement to be higher. Area of reinforcement, if it's higher, then of course you will be having a higher bar. The smaller bar is not going to be sufficient. Okay, so normally we start the foundation normally from 12 mm. Okay, normally for the slab you started from 10. For the foundation normally we start 12 or 14. Okay, for the foundation. Now in this problem I have assumed my reinforcement to be 20 mm. Okay, and I have found my dx using the same equation that we have used in the slab. Dy is going to be equal to dx minus diameter. We said normally the diameters are the same for x and y. Okay, normally are the same for x and y, and we have got our dy to be 490 minus the diameter, which is 20. So we have got our dx and dy. Okay, for the foundation. Any question about finding dx and dy? Any question about finding dx and dy for the foundation? Once again, the depth of the foundation is to be assumed. We are going to work on a trial and error. Okay, trial and error methods. We are going to be assuming a value and we are going to check whether that value is fine or not. Any question about finding dx and dy? Not clear. Okay. Okay. Another thing that we are adding when it comes to foundation, we don't use dx and we don't use dy, and we will see why later on. We are not using dx and dy. Okay, we are using something called d average. Okay, we are using something called d average. Okay, in which we are going to get the average of dx and dy. Okay, and we are going to see later when it comes especially to shear, we are going to see which one to be taken, why we have taken the d average, not dx and dy. Okay, so once again, finding dx and dy, and then one added thing that we are calculating the d average. So we are not designing our element to be resisted mainly by x or y. It is resisted by both of them. That's why we have got d average. Okay. Now, if you see, after we have calculated our area, after our calculation of the area, we need to go and calculate the bending moment. Now, if you remember, we said this is my foundation. The foundation is going to be having a loading from here. There will be pressure from here, if you remember. Okay. And if you remember, we said this will be bending up. Do you remember that we have talked about last class? Or before last class? Last class. Do you remember this thing? And if you remember, we said this is going to be my point load. These are going to be my UDL, which can be converted to be of this way. In which we said the bending moment diagram goes like this. Because of the continuity of the support here in this condition, which will give you a bending moment of this shape. Do you remember all of these from last class? Okay, so once again, this is my foundation. Okay. This is my idealization. We said this is going to be my bending moment. Okay. Now if you see, we said that this location will not bend. Even if you see from the figure, you will see the location which will be bent is after the side of the column. Okay. This is a part where it will bend. This is a part where it will bend. Why? Once again, the loading of the column is very huge. It will not allow you to bend. It will not allow the pressure from the soil to bend the location of the column. Okay. So what we need to do, we need to find the bending moment. Okay, we need to find the bending moment at the face of the support or the face of the column, if you remember. Okay. So we said that this is going to be like this now. Where we are going to have a cantilever. Okay. In which we are going to have a cantilever. Now for us to find the bending moment, which is in this case, for example, we need two things. We need first, okay, if I draw it here in a larger scale, we require two things. We require length and we require the pressure. Okay, or the loading, let's say. Okay. Now the loading which will cause me to go up, is the pressure from the soil. So now I need to calculate the maximum pressure that can be caused by the soil. Okay, so the maximum pressure is calculated as 1950, which is your dead load, multiplied by 1.4 plus my life load multiplied by 1.6. Now, why in this scenario, why we have multiplied by a factor of safety? We have multiplied by a factor of safety because we are designing for the maximum pressure in which we are going to get the reinforcement. And if you remember when I have talked about ultimate limit state and serviceability limit state, I told you whenever we talk about the design of reinforcement, we are referring always to ultimate limit state. Always we are multiplying by a factor of safety. In case of any added loads, my reinforcement should be able to take that particular loading. But for example, when we talk about deflection, we are talking only about the existing load. I will be deflecting, or my element will be deflecting according to the load available now. It will not deflect according to the loading which will be available tomorrow. But when we design the reinforcement, we design it for the critical scenario or the most severe scenario, which is the highest loading. So the highest possible loading is dead load into 1.4 plus life load into 1.6. Okay, so if we multiply 1050 into 1.4, okay, and 300 multiplied by 1.6, we will get 1950. Now, one question should be asked here. If you remember, we have done the service limit state loading, which is SLS, and we have done the ULS, which is ultimate limit state. Service limit state, we didn't multiply by a factor of safety. ULS, we have multiplied by a factor of safety. But you will see one difference between these two now, other than the factor of safety. You will see that the service limit state is going to have the self-weight with it, while ultimate limit state is not going to have. Okay. While we are calculating the ultimate limit state for the foundation, we don't have, or we are not including, let's say, I don't know, it's wrong to say we don't have, but we are not including the self-weight or we are not taking the self-weight into account. Any idea why? Any idea why? Any idea why self-weight is not to be taken into account? Okay. Now, when it comes to the self-weight of the foundation, you will see that the foundation is not going to be loaded at one time. Okay, the foundation is not going to be loaded at one time because we are going to be doing the construction of the floors one by one. Okay, so you will see that first we will put our self-weight. Okay, we will put our self-weight, which is already supported by the soil. Okay, so we have put our self-weight, we have put our foundation, which is including its self-weight. We have kept it in the soil. Now, by that time, already the foundation is settling down. Okay? The foundation is already settling down. Whenever the floors are increasing, you will see that the bending is only going to occur. Okay. Once again, I kept the paper. Okay, I kept the paper on the sides of the. And I brought two tables. I brought one A4 paper, and then I kept it between the two tables. Now you will see whenever I'm going to supply, or whenever I'm going to keep the paper, it will not bend. Okay, it will not bend because it's supported till now. Now, if I go and add extra loads, which are acting as the loads of the columns, you will see that my paper is going to start bending now. Okay, and that's the main reason why we don't take the self-weight of the foundation into account when it comes to bending moment. Okay, when we calculate bending moment, your foundation acts like a paper. So at the beginning, we kept it in the foundation, we kept it in the soil. It will not bend. Whenever we start loading the column, you will see that this particular loading is trying to push down. My capacity of the soil is trying to push up, and because of that, you will see that this particular element is trying to be bending up. Okay, so once again, when it comes to calculation of bending moment, we don't take the self-weight into account because of the foundation is kept in the soil. It will not bend. It will only bend whenever you are applying the loads of the column in reality. Okay. So that's why when we calculate for bending moment, we will not take the self-weight into account. Okay, we will not take the self-weight into account. But when we talk about the pressure, in pressure we are not calculating for bending moment. We are calculating how much load is existing. Okay, so you can see the soil can take up to 1,170 kilonewton per meter square. Any load comes from the foundation should be calculated. It is going to be affecting my capacity of the soil. Okay. Once again, when we talk about the pressure, or when we talk about the ground pressure, we are taking all the loadings from the top. Okay, and we are comparing it with the capacity of the soil. Okay, since there is a weight of the foundation itself, you will see that it will contribute in the ground pressure. But when we talk about bending moment, this particular element, which is the foundation, is already settling, is kept in a soil. It will not bend. When it will start bending, it will start bending whenever we are starting to load the column itself. Okay, so once again, when we are calculating the bending moment, we should take the ultimate limit state, because we said we are designing always our reinforcement for the critical scenario. The second thing, we don't include the self-weight. So now we have found our pressure to be 216.67, which is this one. Okay, so we have found number one. Remaining is number two. For me, once again, to calculate the bending moment, I require the length and the pressure. Pressure has been found to be 216.7. Okay, now this is my foundation, which is 3 meters. You will see that if my column is 0.4, I need to go and calculate this particular length. Because we said bending moment will only act at the center or act at the face of the column. So we need to calculate this particular L. Now, how much is this particular L? This particular L is going to be 1.3 meters. How did we find it? We can find it either by saying 3, which is the full thing, minus 0.4, which is this particular column size, divided by 2, because there are two areas. This is area number 1, this is area number 2. Okay, which will give you 1.3 meters. Or you can say that since this is 3 meters, half of the foundation is going to be 1.5 meters. This is half of the column, which is 0.2. So now this area is going to be 1.5 minus 0.2, which will give you 1.3. Both scenarios are fine. Okay, so now we have got our length. This is in one direction. What about the other direction? You can see for the other direction, once again, it is going to be 1.3. Why? Because it's a square column and it's a square foundation. Now, if it's not a square column and a square foundation, you will see that your lengths are not going to be the same. So here, your length number 1 is going to be different from your length number, is the same with length number 2. But if the dimensions are not the same, the dimensions of the column are not the same, or the dimension of the foundation is not the same or are not the same, you will find your L1 and L2 are not going to be the same values. In that scenario, if you have L1 and L2, which are not the same, in this scenario, it's 1.3 for both of them. So I don't need to design, in this scenario, I don't need to design for 2 bending moments, because my first length and my second length are the same. Now, if your L1 and if your L1 and L2 are close to each other, like for example, we are talking about 1.3 and 1.2, once again, you don't need to go and calculate for both of them. You will take only the highest, and the highest will be supplied in two directions. But when it comes, for example, one is 2 meter and the other one is 0.8, there will be a huge variance when it comes to the bending moment of both scenarios. Your L1 is 2 meter, your L2 is 0.8. So you need to calculate for two bending moments. The first bending moment will be supplied, our first reinforcement will be supplied to resist the first bending moment, and then the second reinforcement will be supplied to resist the second direction bending moment. In this scenario, we have 1.3 and 1.3, so only there will be one L. I don't need to design for both directions. Okay. Once again, if you remember, we said we have it in this way now. This is going to be my foundation, the other side as well. Okay. This length we have found it to be 1.3 meter. This pressure is 216.67 kilonewton per meter square, and then we are designing always for 1 meter width. So finally it is going to be kilonewton per meter. Okay, so 216.67 and then 1.3. If we try to flip it in the way that we normally take our loads, you will see that normally we are having it in this way, and the bending moment for this particular scenario is like this. And how much is the bending moment here? The bending moment is WL square over 2. So once again, what I have done, I have just draw it in a way that we normally draw. Okay, and then I can convert it easily. I can now say that this is going to be my bending moment for the foundation. Okay. Now, how much is the bending moment? The bending moment is WL square over 2, which is for a cantilever. W is your loading, which is here. So it's 216.67. My length is 1.3 meter. Okay. So 216.67 multiplied by 1.3 square divided by 2. We have got our bending moment. So this is the bending moment that we need to design the reinforcement for. So moment, the next step is going to be calculation of K. After calculation of K, we are going to go for Z. After Z, we are going to go for AS. So you can see now here, this particular M is applicable for both directions of X and the other direction of Y. Okay. Now, if both or we have different lengths, then you should be taking into account, if you want an accurate result, you should be taking dx separately and dy separately. The average should be used mainly when it comes to shear reinforcement or shear check, which will be seen later. Okay. Now, in this particular context, or for the study level, even if you have L1 and L2, you can take average. Okay, you can take the D average, which is for the student level now. Okay, so moment is 183.09 multiplied by 10 to the power of 6, as we said when it comes to moment. SU has been given from the beginning to be 35. B is 1000 because we are designing for 1 meter width, something similar to the slab. My D average is 480. We have got it to be 0.023. Okay, 0.023 is a singly reinforced because it's lesser than singly reinforced section because it's lesser than 0.156. Okay. After that, we will go and calculate Z1. The same scenario, D average is going to be used. We have got our Z1. After that, we have got our Z2. And we said from the two, we are going to take the smallest value. So the smallest is 456. After getting our Z, we will go and calculate our area of reinforcement. moment is there, Z is there, and then you have 460 as your reinforcement. We have got it to be 919. We can use either the table which is available in your VS Code, or you can use the method I have told you, which is finding the diameter and then 1000 divided by the assumed spacing. Okay, so we have found it to be 715 as the minimum. My AS required is 919. So if we go and see the okay, if we go and see the last page, you will see that we have 20 mm. So 20 mm bar. The spacing is 300. I have taken. So it is going to give you 1050. Okay, 1050 mm. diameter with 300. Spacing is 1050.
Should be taken to the column, not for slab.
What? Once again, can you
The
repeat?
reinforcement.
Yes.
We
What
should
about it?
take for the column, not for the slab. You'll take you the first table. We should be take the
Okay.
second table.
Why?
Because we calculate for the column.
Which column? We are not designing a column now. We are designing a foundation.
Okay, sorry.
Okay. And you can see clearly. Here it says for you slabs and foundation. Okay. You can see clearly here it's slabs and foundation. And if you want to confirm further, you can see that here it says for you cross-sectional area per meter width. The two elements which are designed only for meter width or for a width of 1 meter as slabs and foundations. Okay. Columns, beams are not designed for 1 meter width. Okay. So we have got our bending moment. I don't think that there is sufficient time to go for shear now. So we will leave shear for the next class. Okay, I don't want to rush things up. Okay, so we'll leave shear to the next class. The only thing what we can do, let me just illustrate for you in Excel, and we will verify, and then I'll open for you as well a sample drawing in which I'm going to show you the foundation layout. Okay, so this is my Excel in which I can design my foundation. There are two types. You have single and you have double. Single is representing isolated foundation. Double is representing combined foundation. Okay, so FCU is 35, FY is 460, density of concrete is 24, bearing pressure is 170. Okay, and we have H of aggregate, size of aggregate, maximum size of aggregate, which is 20. Cover is 50 mm. Soil, if we are calculating the backfill, we require the soil unit weight. Okay, the column size is 400 into 400, and then you can see here we have taken it to be 3000 into 3000. Okay, 3000 into 3000. My dead load is 1000 and my dead load is 1000 and how much we had it? We had it 1050 and 300. So 1050 and then this is 300. And my depth has been taken, overall depth has taken as 550. Now you can see that this is my foundation. This is my foundation. This is my column as well, which is at the center. You can see that I can play with the centricity, whether X or Y. Like for example, I can play with 200. You can see that it has been shifted 500. You can see that we are moving the X direction. So there is a centricity of 500 from the center. You can play as well with the Y. So there is, for example, 700. And you can see now that because of changing the location of the column, you can see that the pressure, ground pressure, has jumped from 91% to 424. 424 means you are exceeding the level of ground pressure. The required, or the soil can take up to 100%. Okay, if you are having something lesser than 100%, it means that you are not failing. If you are having something more than 100%, it means that the soil will not take it. Okay. So what I'm going to do, this is going to be returned as 0 and 0. Now you can see that this turns to be around 90%, okay, or 90.2%. Okay. So now, doing so, if I'm getting 90%, means I have utilized to the maximum. I have utilized my my foundation. Okay. Now, as well, if you are using the Excel, it can make it a bit, easier for you. It can recommend for you the size of the foundation. So you can see here, 2,915 square. So for example, I can go here and say 2,915, 2,900. So you can see now 95%. Okay, even 2,905, 2,905. Okay, so you can see that utilization is around 96%. Okay. For bending moment, if we are keeping it to be 3,000, you can see here that the bending moment is 549.3. And how much we have got our bending moment? We have got our bending moment to be 183.09. Okay, we have got our bending moment to be 183.09, but the Excel has found it to be 549. Now the Excel will calculate it for 3 meters. It will not be calculating it for 1 meter. Okay, so if you remember, once again, my bending moment has been calculated for a width of 1 meter. So 183.09 is only for 1 meter. If we are going to multiply it for 3 meters, you will see that it's going to be 549.27, which is the same as your Excel, approximately 549. Okay. And then, of course, the D will differ from here to here because the Excel will be taking X separately and Y separately. The other thing, the Excel has taken this diameter to be 16, not 20. So, of course, they will differ in terms of value of reinforcement. Okay. And that is for today's session. If you have any question, you can ask. The last thing, before leaving, the last thing that I want to show you is the sample detailing. So this is a foundation layout. This is a problem that I have brought for you, in which we try to solve today, where the width is 2.1, and you can see according to that particular loading, in which the loading were the same as well. I have got your real loading, because this is a twin villa. Okay, it's a twin villa. So we have got one column in the first villa, the second column in the other villa. Okay, so these are my combined foundation. This is my combined foundation with the width of 2.1. Now you can see here the flexible sheet that Ms. Mazoon has told you, in which you can see if they are not overlapping, but they are having almost zero distance between one foundation to another foundation, then normally here in Oman, most of the scenarios, we don't go for a combined foundation. Okay, we go for isolated foundation with flexible sheets. Okay, so you can see here, between the first foundation and the other foundation, there is a flexible sheet of 20 mm. Same thing here. Whenever there is an interaction between foundations, we have flexible sheets. But of course, you can go for a combined or a raft foundation whenever is required. But if you want an economy design, which will be taken by the owners, then you should try to reduce the reinforcement. Okay. These are the schedule. Okay, this is the schedule. In this way, you should write your foundation. You can see here we have F1, F2, F3, F4, and then CF. F is representing foundation, regular isolated foundation. CF is combined foundation. Okay, and you can see here. Okay, you can see here, for example, the size of the RCC, and we have size of PCC. Size of RCC, we are talking about length, width, and then depth. Okay, so length, width, and depth. Now the same scenario we are having for the BCC. You can see that this is length, width, and then depth. Okay, now the BCC is always going to be 1 millimeter extra from each side. So if we are having 1700 is the RCC, I'll take 100 millimeter from the right, 100 millimeter from the left. That will give me 1900. 2100. Once again, 100 millimeter from the left, 100 millimeter from the right. Okay, that will give you 2300. So we are taking 100 mm extra than the size of the RCC. That's going to be the size of your PCC. I'm taking 100 mm extension from all the sides, and the depth is going to be 100 mm. Okay, and then you have bottom reinforcement, top reinforcement. Of course, when it comes to isolated foundation, you can see that the diagram of bending moment is either going up or down only. It does not have an up and down. So in that scenario, you will be having only one side reinforcement, which is going to be bottom. Okay. Now in a combined foundation, you will be having top bending moment and bottom bending moment, and because of that, you will be having bottom and top reinforcement. Okay. So this is 12, which is diameter. 200 is the spacing. Okay. So as I told you, you can start from 12 as well. 300 is not that recommended by the municipality. Even if your design is correct and you are using 300, normally municipality will push you to reduce the spacing, means increasing the reinforcement, to avoid any problems coming from the client side. The client can go and try to demand later on increasing another floor. Okay, so to avoid any issues later on, because eventually the designer is the final responsible person about the design. Municipality will approve your design, but you are having the full responsibility if anything happens. Okay, as a designer, I mean. This is what Ms. Khawla or Ms. Mazoon was saying for you when it comes to the neighbor column. Okay, this is the neighbor column, and you can see whenever we are talking about the neighbor column here, we are extending a beam. Okay, we are extending a beam here, which is called a strap beam or an inverted beam in this scenario. Okay, it's called inverted beam or a strap beam. Inverted beam, it means that it's not going to go down as a regular beam, it's going to go up. Okay, that's an inverted beam, which is very important to be known. Doing that, we have finished today's session. if you have any question, then you are free to ask. If you don't have any question, then we have finished today's session.